So last time we ended with an example where we were comparing a 20% interest rate with different kinds of compounding. And just remind me of the numbers here. So we had $1,000 that was 20% and simple interest. And we looked at it over 5 years and over 10 years. And then we had $1,000, 20% interest, compounded. Did you look at daily?
Yeah.
5 years, 10 years. Remind me what the numbers were here.
2,000.
I think this was 2,000. Remember 10 years it was 4,000 something. And then this was 2,717, and this was 7385. Right. So we kind of saw here that this guy pretty much jumps by the same amount. So this guy here jumps by.
It was
3,000, not 4,000.
No, for the
2 and 3.
So this guy jumped by pretty much 1,000 every 5 years. This guy here, he jumped by like 1717 in the first 5, and it jumped larger. This jumped, ballparking it here, 4,600 in the second 5 years. Right, and this was the miracle of compound interest. Of course, it's only a miracle if you don't understand what an exponential function is. So this one keeps getting increased by more and more over time, whereas this one increases by some fixed value over time. The difference being how the interest was assessed. Simple just means it's always assessed based on the original amount. So we're always charging that 20% on this 1,000. Whereas over here, we're charging that 20% on the 1,000 plus whatever interest is gaining over time. And as you can see, it grows bigger and bigger and bigger. So this guy we saw grew like a straight line, whereas this guy we saw grew like an exponential function. It gets steeper and steeper over time. Okay? And that was just an illustration of how something like, well, the reason why we did that was I just wanted to illustrate how something like a credit card bill would grow versus how something like a car loan would grow. These are two very different things, and it's one of the reasons why a lot of people get into credit card debt and that sort of debt. They get in trouble with student loans and things of that sort. It kind of sneaks up on you because you just don't realize what's actually going on. I mean, in your mind's going to think like this, whereas what's really happening is that. Okay, and at this point, I just want to make a disclaimer. I'm not trying to demonize credit cards or anything like that, because in fact, I would say in an economy like the American economy or anything based on capitalism and credit scores and all that sort of stuff, it's better for most people to have credit cards than not, right? So chances are having a credit card is a good idea. It's just that you don't want it to get out of control. That's the secret, right? But there are many benefits to having a credit card, including one that's more relevant in these days. You know, people like stealing your identity and stuff. Usually, if someone spends your credit card money and it's not you, you can kind of get that back. Whereas if they spend money on because they stole your debit card number, that's kind of it's harder to get back. Okay, so not demonizing credit cards or anything, but I do want you to understand how loans like credit card loans operate. And you have to understand that there's a very big difference between the two. And it's something that's, in the short term, it's not very noticeable, but over time it can really build up and compound. pun intended. Okay, so that's where we kind of ended, and I don't think I wanted to do any more examples on that per se, but I wanted to talk about a useful way to come, before that I'm going to talk about a different kind of interest. Now, let's move on to another kind of interest. Then we're going to look at a nice way to compare them. And this is continuously compounded interest. That's a whole other category. So we looked at simple interest, compounded interest, and there's something called continuously compounded interest. And this is really just a kind of, it's like compounded interest on steroids. And so here's the, let's look at the thought experiment. So here's the idea. If you deposit, say $1 in an account, and let's suppose that this account gains 100% interest rate. Right? So worse than your credit card company. Okay? So here's something that's growing at 100% interest rate. Okay? So that's bringing it kind of to the extreme here. And compounded. Now here's why it's a thought experiment, because this can't actually happen in real life. It's more of a theoretical idea. Let's compound this an infinite number of times. How often is an infinite number of times? Every day? No, more. Every second? No, more. Every millisecond? No, more. Every 0.000000001 second? No, more than that, right? Whatever number you pick, we're doing it more than that, no matter how big the number is, right? So we're theoretically going like, this person really wants to steal your money, okay? They're charging 100% interest rate, compounded every moment of every second of every day of every week of every year. Crazy, right? So we're doing this guy on steroids, right? This thing. This function, we're just like, we're going ham. Okay, so now, here's the question. How much would you have at the end of 1 year? So that's the question. How much do you think? This kind of idea, but we're really going all out here. In other words, we're using our compound interest formula, where t equals 1 and our n, we're letting it shoot off to infinity. So the power here is going off to infinity, right? So where, and of course, p is $1 and r is 1, 100% interest rate. And so we want to know what's going to happen if I take 1 times 1 plus 1 over n raised to the nth power and let n go off to infinity. What would that value actually be? What do you think? It's a guess. Infinite amount of dollars. Yeah?
We approach 1 because n is
Well, it can't be 1 because you started with 1 and you're adding interest to it. So it's definitely bigger than 1. For sure. It's E. So those of you who know about it will actually know what the answer to this is if you've seen calculus before. It turns out the answer is going to be roughly $2.72. It doesn't go off to infinity, believe it or not. And that's actually short for 2.718281 da da da. It's a non-repeating decimal. So you can't ever write it down in its entirety. It's what we call an irrational number. But it's 2.7 something would be the answer to that question, right? Which is surprising the first time you actually see it, right? I mean, this was actually developed before the days of where calculus was a thing, and this number, and here's how we'd actually write it down. So we have 1 plus 1 over n raised to the n, this guy. Now if you want to let n approach infinity, you kind of write this little thing here, limit as n approaches infinity of this, and it's equal to, the number is called e. Okay. Now, this is a calculus idea, so if you don't understand what this means, don't worry about it right now. In 1109, you'll get very comfortable with this guy. Okay. So you have this sort of expression, and you're letting the n approach infinity. It turns out it does not go off to infinity, even though it's an exponential function. It actually, and the reason why it doesn't go off to infinity is because we're actually stopping the process after 1 year. And so it actually approaches this number called e, which is 2.718, etc. And why is it called e? It's named after a mathematician. He's Swiss. Anyone knows his name?
Is it Euler?
Euler. That's correct. A lot of people pronounce it Euler. It's not Euler, it's pronounced Euler. Euler? That's how it's pronounced. Now, this guy is a specimen, right? He is very unique among mathematicians. He is one of the few people in antiquity that was very prolific in his old age. It turns out that most of the, well, a lot of the foundation of our mathematical knowledge that we have today was invented, a long time ago. But it's invented by very young people in general, right? Young people contribute to mathematics in general. That's kind of changing these days, but before, most people, late teens, early 20s, they give us these grand mathematical theories that we're still studying hundreds of years later. Euler was one of the few people where, yeah, even into his old age, after he was going blind, he was still just cranking out mathematical theorems. He was very prolific. And now it's at the point where there's so many things named after Euler, it's not even funny. If you go and you talk about, use that theorem that Euler came up with, people will ask you which one, right? It's that. He's that big of a guy, and he actually has a number named after him. So in this class and in your calculus class, whenever you see E, it's not a letter, it's not a variable, it's representing a number. It's kind of like pi. When you see the symbol pi, it's a number, 3.1415, all that kind of stuff. Okay? So there is this number, and where this number actually comes from is this compound interest idea. You kind of take compound interest on steroids, 100% interest rate, an infinite amount of times per year compounded, and you get this number. And if you put a little x here, y equals e to the x, that gives you an exponential function. And most people consider that the most important function in mathematics. But again, that's calculus where you'll start to be introduced to that guy. But you get this guy e. Now I did that just to show you where this formula is going to come from. So let's find a formula for this idea. So regular compounded interest. So we're going to start with that. Start with A equals P times 1 plus R over N to the NT. And then we're going to do a little trick here. The idea is I want this to kind of look like that. And there's a little trick. Again, you'll see this in calculus. But if you put a number here in the place of 1, it'll actually go in the power of e. And so knowing that idea, I'm going to actually want to change this formula to something more useful, where I can let my n go to infinity without having to plug in infinity anywhere, because that's kind of silly. Okay, so here's what we are going to do. First of all, I'm going to try to get this I'm going to do a change of variable. So let x equals n over r this would mean your r is equal to, this would mean your n is equal to r times x. This will mean here I would have 1 over x. This would be r times x times t. And this will be 1 plus 1 over x. Now I'm going to use the laws of exponents here, and I'm going to actually shift this x out. Now the laws of exponents tells us that that is what we would get here. And so now the idea is, as n goes to infinity, you'll notice that your x will go to infinity. And so we want this expression to the x rt as x goes to infinity. Now this expression, you'll notice it was the kind of the previous expression I wrote down here, but it has n in the place of x. But it doesn't matter, you're going to get the same number. This part here is going to turn into e. And so we end up with a equals p e to the rt, which I like to call the PERT formula. You guys know PERT, the shampoo? You guys have heard of it? Yeah, it was a big thing when I was a kid. It was like the first shampoo that was like shampoo and conditioner in one. Like how did they come up with that? I mean, I know it's, for you guys it's nothing. Like now they have like 5-in-1 kind of stuff. Oh, wash your hair, your car, your face. You can wash everything. But back in the day, we had to have a different thing to wash everything. You use shampoo, then you have to use conditioner. No, PERT came out like shampoo and conditioner in one. It was like, it wasn't okay. But that's how I remember this, the PERT formula. P e to the rt, right? E, remember, it's a number. It represents that 2 points, blah, blah, blah. And if you get the right kind of calculator, it will be a number in your calculator, so you should make sure that you actually know where to find e. Right, so it'll be a number in your calculator somewhere. So just like how pi is going to be there, e is going to be there. It's a very important number. The r and the t is the same interpretation as before. That's your interest rate as a decimal. That's the time period. P is going to be your principal. A is going to be the amount that the account goes to. But we have this formula here. The PERT formula, or it's the formula for continuously compound interest. What it grows to in the future. So this is another kind of interest. And it's the last kind of interest we'll be looking at. But of course, we're going to do more things with interest, but I just want you to have the basic idea of how these different systems work out. And again, you can't really compound something an infinite amount of times. It's a very theoretical use. We use it very theoretically. So you'll never have a bank, an actual bank using this formula. But one, it's using calculus all the time because it's super important. And we can actually write things in terms of E. Again, that's all calculus. One way in which people use it in finance, though, is as this theoretically limiting value, right? So when they want to imagine the worst case scenario, right? Because we don't know what's happening in the future. But how big could this possibly get? They'll often use this formula. So they'll know it'll never be worse than this, right? So it's a very theoretical value. It's theoretically used in finance all the time. But it's actually directly used in calculus and many other places. Let's do an example. I guess for comparison we can use the same numbers, but the numbers will, you can swap out the numbers at any time. Suppose you deposit $1,000 at 9.5% APR. And you'll see the phrase compounded continuously, or continuously compounded. At 1 year. Let's look at 5 years. 10 years. Just doing all these so we can compare to the numbers we got previously. So again, a very simple kind of question here, and I will be asking questions like this on the first test. Probably have one problem where I ask several of these. So you can have, okay, you deposit $1,000 at this APR, and I can tell you, oh, simple interest is charged. Or I can tell you it's compounded a certain number of times per year, compounded semi-annually, compounded quarterly, or whatever. Or I can say compounded continuously. Once you see the phrase compounded continuously, it means this is the formula you're supposed to use, not either of the two previous formulas. So we look at A after 1 year. So here we have P is equal to 1,000. We have T is equal to 1. We have R is equal to 0.095. So this means that the amount we will have is going to be 1,000 E. Let me write it down. Like I said, if you see a new form for the first time, you should probably write it down every time you're going to use it. That's how you're going to remember it. To the 0.095. So here's the opportunity for you to figure out where that number is on your calculator. So try to find it now. And once you find it, tell me what you get. is not going to be much different. Maybe someone else can do this one. So for here, p is equal to 1,000, t is equal to 5, r is the same, 0.095. So here I want to make sure that you know how to actually get this in the power. Remember, you have to put the caret and you have to put in parentheses this times that, close parentheses. Tell me what that is. And anyone get this one? What's this? Yeah?
1,099.66.
1,099.66. Do you have any people who concur, agree? So you might remember with simple interest we got 10.95 or something like that for this one. So here we got an extra $4 out of it, sort of an extra $3. And again, doesn't seem like a big deal after 1 year, but over time it'll change a lot. After 5 years, yeah.
$1,608.20.
608.
8.
Okay, rounded to 2 decimal places. So you see, after 5 years, we're adding like 600 something. And after 10?
I got 20.
I got 2.585.
2.5?
2.585.
Come on, go again.
2.585.
2585.71.
0.71.
So those are the years. So that's how an account will grow if interest is compounded continuously. Just to make a note here, because we're not having any quizzes in this class, so when it comes to test time, I want you guys to know what I expect to see when you're writing things down. So just as a general note here, when doing examples, I will write them out the way I expect you to write them out. So that's just a general tip there. So when we're giving, when I'm giving you a test and you have to show your work, I want to be able to assess partial credit. So you have to write down enough for me to know you understand what you're doing. And in general, if you want to know, well, how much do I need to write for you to know what I'm, well, pretty much the amount of stuff that I'm writing down, right? So I'll kind of set out the problem as an example of how I expect you to express a solution to a problem, right? So in terms of what you should write when test time comes around, pretty much do as I do on the board. So that's just a general statement. Okay, let's see. Moving on to the next one. Now, what you might notice here, we've seen 3 different kinds of interest so far. Let's look at a nice way to compare them. So, there are times when you are comparing things where the numbers are often very close to each other, and you're actually not sure which is best or worst. So you can have something like a dollar amount. Let's say we're comparing 1,000 in each situation. Interest rate, let's say APY, and just type. Okay, so you have $1,000, and let's say the APR is 4.21, and I can say this is compounded monthly. Or I can have 4.39 compounded quarterly. I can have 4.11, and I can say compounded continuously. Say something like 3.99 compounded daily. Now you may want to figure out which scenario will be the best for you if you're trying to grow money, or which one will be worse for you if you're trying to borrow money or something like that. Now, in general, we'd expect this one to give a larger value than that one, and this one to give a larger value than all of these. This one would give a larger value than these two, but not that one. But the interest rates, again, they're very close, and they kind of make it not clear, because in general, this one gives you more than that one, but this interest rate is slightly higher than that interest rate. So to actually figure out who is better, you have to actually go through the formula, right? And you have to plug in, A equals P times 1 plus R over N raised to the NT. You have to do it for each of these, and that can kind of be annoying. You could figure it out, you can brute force it. But there is another way that compares these guys. And sometimes you just neglect to tell you how interest is being computed, but we tell you the interest in some other way. It's not with APR, it's with something else. So, answer this question. We can use what's called the effective interest rate. Or another way to actually talk about this is called the annual percentage yield. Now this is called an APY. I'm going to talk about where this is used in a bit. So, example, let's look at one that we looked at before. $1,000, 9.5% APR compounded. What did we do? Did we do quarterly for 1 year?
Yeah.
We did that quarterly for 1 year. What did it end up with?
$1,098.44.
Okay, so this means we gained $98.44 in interest, right? Over 1 year. Now, 944 is what percent of 1,000? You know how to figure that out? Well, you pretty much divide by 1,000. It's going to be like 9.8.
9.8.
Yeah, percent. Going to be 9.84%, right? Now, I want you to notice the interest rate that was quoted to you is 9.5. But if you want to talk about, let's get down to it, really how much interest did I get at the end of the year? Effectively, I got 9.8, right? So that 9.5 turned into 9.8 because I was compounding quarterly. So my interest was gaining some interest for me, and that this allowed me to squeeze out an extra 0.3%. Okay. So this guy in this case would be called the effective interest rate. Another way to call it would be the APY. Okay. Now, all these different situations, we can actually talk about all of them all at once by just putting another column here called the APY. So you won't necessarily have to go through all the calculations and crunch the numbers. If you want to know who is better, you would look for who has the biggest APY, right? So if you can somehow get to this number, that will be better for us. And we can use this number to compare across different ways of assessing interest. And so, here's how we're going to do it. So, APY. This looks at effective interest. Gained per year. So, which means you kind of always set t equals 1 in this scenario, right? So whenever someone quotes APY to you, they're always thinking on an annual basis, right? It's never going to be thought of in any other way. Okay? So, in that sense, the compounded way of compounding annually ends up being equal to the simple interest. And so how did we actually compute this guy? So this means that if I have some principal times 1 plus let's just use I. Divided n times per year. Let's use R for rate. So this is the I for compound interest. So the idea is you want to kind of think of different kinds of interest as if they were simple interest. So tell me what the interest gained over a year. And so we want the simple interest way to describe the total interest. And what you can do then is you can actually just solve this equation for R. So you would divide both sides by P, and you would subtract 1. And so this means, in this case, when I'm thinking of APY, it's going to look like 1 plus I to the n minus 1. And my I in the compound way is actually R over n. And that's going to give you your APY. If you want to calculate it as a percentage, you can actually multiply it by 100%, because that's going to give you the decimal value for the percentage. So this is a formula for APY. we'll do an example of this next time because I believe. Oh, we actually have about 4. I think we can do that. Let's actually do this for this one.
I have a question.
Yes.
What's the 100% for at the end?
Oh, so just write it as a percentage because this will give you the decimal value of the percentage.
So just multiply by. Alright, thank you.
Right? So if this gives you like 0.095, if you multiply that by 100, you get 9.5%. Let's calculate the APY for this situation. So here, just to not run. So let's say you're in this situation and you want to know what is the effective interest rate at the end of the year. What you would do is you'd find the APY. This is going to be 1 plus R over N to the N minus 1 times 100%. So in this case, this is going to be 1 plus 0.095. I'm going to divide that by 4 because it's quarterly. And 4 is going to go here, 1, and then times that by 100%. Put it over here. Now if you actually compute this value, So take 0.095 divided by 4, then add 1, then raise that to the 4th, then subtract 1. So you have to follow PEMDAS. What would you actually get here? Anyone do it? Yeah?
8.64.
Yeah? It should be the same that we had before. You should get 9.8 something, right? Right, you should be able to get to that answer just by doing that one form, this formula. Now if you don't, it means you're not using the calculator correctly. You want to figure out how to use it correctly before the test day. Yeah? Usually if we're dealing with finances, round to 2 because of the cents. We'll just do that as a standard. Now, you'll notice here, now here's something you can notice, just to mention, we're not going to do another example, but start noticing. Look at your credit card bills and look at your banks when they're offering some kind of savings account or CD or high interest savings account. People investing firms, they use the APY. So they're going to tell you, if you invest your money with us, it's going to grow by this percentage. And because the APY is going to be bigger than this number, you're going to like, oh my God, I'm getting 9.8. But really, they're compounding you at something smaller. They're just going to quote this price to you to get your money. Whereas if you talk about loaning firms, like credit cards and etc., they tend to use APR. They're not going to scare you with the highest interest rate because that's what your debt is growing at. They're going to tell you this interest rate. So you'll notice if you look at your credit card statement, it tells you APR. Whereas if you look at a statement for your savings account, it's going to tell you APY. Start noticing when you go around and reading signs. When a bank is advertising a CD, they'll say APY, not APR. Start noticing. You'll notice it. People use these different numbers because the APY tends to be higher than the APR. So if you're investing money, they're going to want to advertise this. If you're borrowing money, they're going to advertise that. And you should be aware that just because your credit card tells you they're charging you 21%, it's actually a little bit higher effectively per year. And then that gets compounded every year. So we'll stop there. And yeah, next time we'll deal with the idea of making continuous payments. So here we were doing one payment, we're gonna look at extending this next time. I will see you guys on Friday.
Homework is on Jupiter? Yeah.
Homework will be through the web work.
Okay, that's what.
Yeah, but make sure you can log in.